Good morning. Today is our last lecture in this semester. And now you are doing the test. Now that I'm lecturing this, you are doing the test. And I'm lecturing. But look, I could have squeezed, so to say, this material during past lecture. But then maybe it would be more difficult for you to understand. Just as a service to you, not that I'm volunteer to give you something more. Just as a service to you, dedicated service to you, I decided that I will not be in a hurry in past lecture, and today I will finish. Now, I will not cover the whole lecture. Why? Because I do not want to give you additional material beyond the syllabus. Pay attention. What is left is this energy methods. The rest I have V. At the end of this lecture, I will put V here, and we will be done with this course. Okay? So this lecture will continue maybe half hour, maybe 40 minutes, but not entire period. So we started Castigliano's theorem. Alberto Castigliano, 1879, he developed his theorems, two theorems, but we will deal only with one of them. And I mentioned that I have some connection with him because I was appointed as Alberto Castigliano visiting professor at University of Palermo. Okay, to derive Castigliano's second theorem, not the first, but look, if you want to know what was the first theorem, then when you will be working already as an engineer, you will hopefully continue your education, you will not be done. And you will be able to learn what is the first theorem, etc. But now we are dealing with the second theorem. So there are n forces, n. Why not to say how much is n? Okay, because we don't know. Each of you might have different n. Some person may have one force, other person may have 10 forces. And other people, like in problem number 3, in the project number 1, you had 70 forces. So P sub 1, P sub 2, P sub n. Then energy, okay. According to the conservation of energy theorem, the external work done by these forces is equal to the internal. So this is external work is transforming into internal strain energy stored in the body. Okay? So external work is function of the external loads. Like that is summation P dx. Loads are acting upon appropriate displacements, and then summation. So internal work is also a function then of the external loads. U sub I equals U sub E, external, and that is a function. We don't know which function. It depends on the problem. In every problem, there is a different function. F of P1, P2, P sub n. Okay, then now if any one of the external forces, say P sub j, only P sub j, so j is fixed. Let us say if I have 79 forces, then j may be 59. So force 59 is increased by a differential amount dpj. The internal work also will be increased, such that strain energy becomes, look please, we had U sub I, strain energy was internal, U sub I. So it will get an increment du sub I. So what is this? That is U sub I plus derivative, that is a rate of change, times the change of the load. So that is very, very simple. So we write this expression. Now we continue. This value, however, this value means this one, this expression, will not depend on sequence in which the n forces are applied to the body. For example, we could apply dpj to the body first, then apply the loads P1, P2, P sub n. Okay? In this case, this dpj would cause the body to displace a differential amount d delta j in the direction of dpj. Okay, by virtue of the external work, then equals 1/2 pj delta j. Maybe I should increase or not. I think that I should increase, yes, so that you will see better. Yes. In this case, dp sub j would cause the body to displace a differential amount d delta j in the direction of dpj. That is a change of the load. And this equals 1/2 pj delta j. The increment of strain energy would be this amount, half dpj, that is a load change, d delta j. This quantity, however, is a second order differential. Why? Because 1/2 dpj d delta j. So that is this with d differential, and that is also d delta j. So small quantity times small quantity. So that is small quantity times small quantity. So this is second order differential and may be neglected. Further, application of the loads P1, P2, Pn causes dpj to move through the displacement delta j. So then strain energy becomes ui plus dui, then ui plus dpj delta j. Paying attention, there is no 1/2 because these loads were applied already. Here as above, U sub I is an internal strain energy in the body caused by loads P1, P2, Pn, and dpj delta j is an additional strain energy caused by dpj. In summary, 43 represents the strain energy in the body determined by first applying loads P and then dpj, the previous one, with 1/2. Here, this is strain energy determined first by applying dpj, and then loads P1, P2, Pn. These two equations must be equal. Okay? So I will give you this expression and this expression. So I will write it down so that 1443. I will write it down. U sub j plus d u sub, u internal I, u sub I equals u sub I plus du sub I dpj dpj. Now we will write 1444. I will rewrite it. U sub I plus du sub I equals u sub I plus dpj delta j. Okay, so now these expressions must be equal. Okay, so this equals this equals this equals this. So that means that these guys should equal these guys. So therefore, this guy equals this one. Okay, must equal. So that is 26.1, 26.2a. So that is 26.2b. To be or not to be? To be. Our answer to coronavirus is to be. Okay, so therefore we get delta J equals dui dpj. which is a proof. So that was a very short theorem. The displacement delta J in the direction of Pj equal to the first partial derivative of the strain energy with respect to Pj. Okay, so there is now discussion. Castigliano's second theorem, that is this. That is this theorem. Is a statement regarding the body's compatibility requirements, since it is a condition related to the displacement. Also, the above derivation requires that only conservative forces be considered in the analysis, means no friction. No friction force. Is considered. These forces can be applied to any order, and furthermore, they do work that is independent on the path and therefore create no energy loss. So friction creates energy loss. As long as a material has linear elastic behavior, the applied forces will be conservative and the theorem is valid. Castigliano's first theorem is similar to the second theorem. However, it relates the load Pj to the partial derivative, that is, Pj equals dui dPj. The proof is similar and given above. This theorem is another way of expressing equilibrium requirements for the body. However, it has limited application and therefore it will not be discussed here. Still, I recommend you when you work, and if the work allows you to expand your knowledge, and I personally think that every American company and every world company should demand workers to spend at least 1 hour a day on self-improvement, mathematically, in mechanics, and in other fields. Or that could be 1 free day. I envision as a work environment in which, say, people work Monday, Tuesdays, and Wednesday is a study day, and then Thursday, Friday. This day will come. By the way, in France, partially it is there. They have 35-hour work week. Okay, what is a procedure for analysis? Procedure for analysis is as follows. Place a force P on the truss, for example, if you talk about truss, at the joint where the displacement is to be determined. The force is assumed to have a variable magnitude and should be directed along the line of action of the displacement. Does not make sense to apply a load in another direction that you are not interested in. Determine the force N, forces, axial forces, in each member in terms of both actual numerical loads and the variable load P. Assume that tensile forces are positive and compressive forces are negative. Okay, this guy is, Hibbeler is repeating this sentence, and book becomes heavier and price becomes bigger. But we already agreed that tensile forces are positive and compressive forces are negative. We do not have to assume this. That is what is done in entire book. Find the respective partial derivative, dn, dp for each member. After n and dn, dp have been determined, assign p its numerical value if it has actually replaced the real force in the truss. Otherwise, set p equal to 0. Then apply Castigliano's second theorem to determine the desired displacement delta. It is important to retain the algebraic signs. Algebraic signs, of course, that is a repetition of that. Because if n is positive when it is tension and n is negative when it is compression, that means that we talk about algebraic sum. negative terms we should not change into positive. When substituting these terms into equation, if the resultant sum n dn dp is positive, delta is the same direction as p. If it is negative, if the negative value results, delta is opposite. Okay, let us consider an example. Example is like this. We have a truss, 1, 2, 3, 4, 4-member truss. So today we will deal only with trusses and beams, and we will be done. I'm not going to add additional material because it is, I think, unfair. That is additional lecture. Yes, I did it for your success in the course, but still I should not add additional material that I would love to add naturally. Determine the vertical displacement at joint C. Vertical, that means in this direction. Of the steel truss shown in this figure. The cross-sectional area of each member equals A, 400 millimeters square. And steel's elastic modulus equals 200 gigapascals. Okay, you may ask, come on, this is millimeter square, this is gigapascal. So what units are there? Yeah, that is a mixed units here he is using. But if we would have said in meters, that would be a very small quantity. And we cannot visualize. It's difficult to visualize very small quantities. So therefore, they are using mixed system. External force P. Vertical force P is applied to the truss at joint C. That is a variable. That is because I want to find in this direction, I'm applying this load P. And because it is not here at the end of this process, we will remove it. Okay, so we go from 0, from P equals 0, to P equals 0. But here we will use Castigliano's theorem. Okay, this we did also in differential equations. Differential equation was real, 26(3)b. ODEs, okay? ODE is a real function and derivatives collection, like a ball. Okay, so for example, we have here f double prime, then f prime, then f. Let us say this 3 times, that is 4 times, that is 20 times. Okay, then we have 3f double prime plus 4f prime plus 20f equals 0. So that is a soup of functions and derivatives. So everything is real. There is no imaginary numbers. Then I substitute f equals e in power c in power rt. Then I will get 3r squared plus 4r plus 20 equals 0. Then let us find the roots. R equals minus 4 plus minus 16 minus 4 times 3 times 20 divided by 6. Okay, that is minus 4 plus minus, then 16 minus, that is 60, 240 divided by 6. That equals minus 4 plus minus 224, 6. Okay, so suddenly we get i's. That is minus 4 plus minus I, 224, 6. So from reality, we go this, then we are using Euler's formula, IT equals cosinus t plus I sine t. And we get real expression, F equals some real expression. So we go from reality to reality, but through complex numbers, that is complex number. Analogously, exactly analogously, that is what we do. There is no P, but I'm adding P. So there is no P in the beginning. I'm adding this P. Later, I will put P equals 0. You may say, come on, that really, someone will say it is fancy. Someone may say, come on, it's not clever at all. That is some gimmick. No, my dear friends, it's not gimmick. That is a very useful tool. Gimmicks can be very useful. Something that looks like gimmicks. That may be very, very useful. Okay, we continue. So then, look, please, I added this first P. Means that, look, please, paradoxical. I complicated the problem. Why? Because, look, please, there were just one force. Here, suddenly, I added another force. So now I have two forces. You may say, how it is possible? Yes, sometimes you complicate the problem in order later to simplify drastically. Okay, so then look, please. That is P, that is a log. So look, please. That is 100, that is P. So reactions here, reactions equals 100 kilonewtons plus P. This is 200 kilonewtons plus P. That is 200 kilonewtons plus P, but in different directions. That is easy to find. Then we are making cuts. This cut, so that is this cut. And then this cut. Cut 1, cut 2. We don't need to do cut here because the force here equals this one. Okay, that is the third cut. So then we get, look please. In member AB, n equals minus 100. That is due to forces only. Due to original forces only. Then in BC, 141.4. AC, then minus 141.4 plus 1414P. Oh, that is the loads for both, due to both. CD equals 200P. Now, derivative of this expression equals 0. Derivative of this equals 0. Derivative equals minus 1414. Derivative equals, with respect to P1. Now, what is the value of n when P equals 0? Okay, then it's minus 100, that is plus 141.4, minus 141.4, that is 200. Lengths are, proper lengths are 4, 2, 8, 2, 8, 2, 8, 2, 8, 2. Now, load times derivative times L equals this. So then, Castigliano's second theorem, 1446. Gives us the following expression. Delta CV equals sum of n, dn dp, LAE, 965.6 0.7 kilonewton over meters divided by AE. AE is this value, we get 0.01207 meters, or 12.1 millimeters. This solution to be compared with example 14.1 using virtual work method. Naturally, the same result. Any questions? Okay, Castigliano's theorem we would like to apply to the beams. The internal strain energy for the beam caused by both bending and shear. However, as pointed, the beam is long and slender. If beam is long and slender, the strain energy due to shear can be neglected. So therefore, strain energy will be moment squared dx over 2EI. Now, if I do derivation, will be d dp of m squared dx 2EI. Okay, we don't need to square. We can do, we do not need to square first this and then differentiate. We can differentiate the square. Will be then 2 times, okay? Equals d dp will be 2 times, and then integral 2EI m, and then dm dp, then dx. But these two and these two are canceling each other, and we get this dx over EI, m times dm dp. Okay? Now here, delta is the displacement of the point caused by the real loads acting on the beam. P is external force of variable magnitude. Internal moment of the beam expressed as a function of x and caused by both P and actual loads. E modulus of elasticity, I moment of inertia. Analogously, theta, for theta, if I want slope, then theta equals m dm, dm prime, dx EI. There, before that was, look please, I will write it down. Delta equals m dm dp dx over EI from 0 to L. So that is this, we want displacement, I have to differentiate with respect to P. If I want the slope, I should differentiate with respect to moment. Okay, if I want to include everything, like axial load, shear, torsion, okay, if they contribute a lot. So you have to calculate. If this energy, if energy of axial load is comparable to energy due to shear, and it is comparable to energy due to torsion. And this is comparable, of course, energy due to bending. Then all should be, that is if. Okay? If, then we have to take them into account. So then delta will be summation n dn dp L AE, that is due to axial loads. Okay, that is due to shear. That is axial loads. That is bending. That is torsion. Okay. Any questions? So I will consider the procedure for analysis. Okay, this procedure is important because it tells us what should be done. External force or couple moment M prime. So these are additional things that we are introducing. We are complicating, as it were. I will write as it were. If the slope of tangent is determined, then we have to add this one, couple moment. They have a variable magnitude. It means that is why I can differentiate with respect to them. I cannot put P equals 100 or 200. Then I cannot differentiate with respect to 100. It should be variable. Establish appropriate coordinate system that are valid within regions of the beam where there is no discontinuity of force, distributed load, or couple moment. Determine the internal moments, M, as a function of X, actual numerical loads, and P and M prime. Then calculate these derivatives. Then of course, algebraic signs should be respected. We understand this as we are actually, all of you are applied mathematicians. We all are applied mathematicians. Okay, engineers are applied mathematicians. Without mathematics being applied, that is not engineering. Examples. Determine the displacement of point B of the beam shown here. Okay, pay attention. We do not say find the displacement and then substitute the value at x equals 0. So I'm adding this force, P. Then bending moment will be minus, that is W, that is an external load. That is variable load. That is like Romeo. Comes uninvited. To Juliet's party. If you remember from Romeo and Juliet, two families, Capuletti and Montague, were enemies of each other. Naturally, they would not invite anyone from another family to their party. So there we are adding this P. So then dm dp will be minus x. So if I put p equals 0, then I'm getting minus wx squared over 2, and dm dp equals minus x. So I'm integrating delta b equals integral from 0 to L, m, dm dp dx ei, minus wx squared, that is m, then minus x, dm dp. Over ei. WL in force power 8 ei. Beautiful. Beautiful result, fast, nice and dandy. That is what imagination does. You see, do you remember Einstein said, imagination is more important than knowledge. Suddenly, look please, we don't need integration of differential equations, satisfy boundary conditions, finding constants, substituting constants back, then substituting x equals 0. Suddenly, in few lines, we are finding the same result. Another example. Determine the slope at point B. That is B, anywhere, of this beam. Okay, then I'm putting external moment here. So I'm complicating. That is now our Romeo is this one, M prime. So here, of course, using method of sections or method of cuts, internal moments are determined like this. So here, that is two coordinate systems I'm using, x1 from here and x2 from there. So in the first part, okay, will be minus p times x, dm prime, dm1, dm prime is 0 because there is, this moment is still not applied, so naturally it's 0. In the second part, m2, that is m prime, minus p, then L over 2 plus x2. Derivative of this with respect to m prime equals 1. Now we are using Castigliano's second theorem. M dm dm prime, dx over ei. So the minus px, that is moment. 0 derivative, that is this one. Okay, that is gone. Then here we have moment equals PL over, that is this moment. Derivative equals this one, that is this one. 3PL 8E minus 8ER. Any questions? Also very simple. I would say to the point. Okay. Okay, let us do chapter review in this transparency. When a force coupled moment acts on a deformable body, it will do external work when it displaces or rotates. Internal stresses produced in the body also undergo displacement, thereby creating elastic strain energy that is stored in the material. The conservation of energy states that if the external work done by loading is equal to the internal static strain energy produced by the stresses in the body. That is this one. Okay, with elastic impact we did not consider, so we do not consider this. The principle of virtual work can be used to determine displacement of joint on a truss or a slope of the displacement of points on the beam. It requires placing an external virtual unit force at the point where displacement is to be determined. External virtual work that is produced by the external loading is then equated to the internal virtual strain energy of the structure. 1 times delta equals this, or 1 times delta equals small m, capital M, EI. M is created by unit value, unit force. Castigliano's second theorem can be also used to determine the displacement of a joint on a truss or the slope of the displacement at a point on a beam. Here a variable force P is placed on the point where the displacement is to be determined. The internal loading is then determined as a function of Pm prime, and the partial derivative is determined. So when we say OP or this, or, and this also, or, Castellano's second theorem is then applied like this. Delta equals, that is for truss. That is for displacement of the beam. That is for the slope of deflection of the beam. Okay. Let me Okay, all this should be done naturally if we are designing a good, reliable structure. Look, please, not like this. If you have to design such a system, you don't need not finite elements, not Castigliano's theorem, not virtual force method. You just do whatever, and it either works or not, etc. We are using these methodologies for very important things. And for displacements, we actually got 3 methods for displacements, just one displacement. So we have one method is ordinary differential equation, integration, singularity functions. Is that right? Second, yeah, let me see, where is my last transparency? Okay, then second is virtual displacements method. Third is Castigliano's second theorem. Okay? Which one to use? Okay? Whichever is preferred by you. We have a choice. That is like going to Starbucks. I hope that we will be able to go to Starbucks or other places. You can have this cappuccino, espresso, or cafe latte, etc. You are choosing whatever you want. It's always good to have choice. And this is manifesting by these 3 possibilities. These are, of course, simple methods, very simple methods. Okay, and I'm showing you last transparency or last slide this semester, and that is this one. I covered the energy method, so I covered everything absolutely. I tremendously enjoyed working with you, with each of you. I wish you much success in your future professional endeavors. Look, when coronavirus is over, please stop by, say hi. Even so, you will be not studying with me, you will be studying something else. Just say hi, and we will remember these old, difficult times, of trying times that we all passed, I hope, successfully. I wish you all the best in life. Thank you very much for your attention throughout the whole semester and very nice interactions that I had with each of you. Much success.